The topic is deterministic simulation testing, and you already sort of warmed up the audience how many people know about that. This is actually for me a fun thing to talk about because I've been following this type of sort of method of testing for a long time. And at work we happened to do a rewrite, and we decided, okay, we're going to try this out. So this, I at the same time actually consider myself kind of a newbie to this. So we've been doing this in practice for 2 months. But I think there's already sort of kind of interesting findings to share with everyone. So actually, before I continue, it's also a quick round. Like, how many of you are programming systems like using Rust or SIG or C, or and the rest are using JavaScript, Python? Okay, so but this is going to be an interesting audience as well. But I think many of these things are probably at least interesting from sort of the method perspective. I don't know how applicable that is. Most of the examples here are actually in Rust, but you can also learn new languages if you want. So basically, quick outline of this talk. I'm going to first talk about on testing, actually developer testing in a sense. Then I'm going to spend time talking about sort of the, let's say, theory behind DST, so deterministic simulation testing. Then we're going to build our own DST. Actually, I'm going to show a proof of concept that I did, but Juho loves me being in the editor, so we will be in the editor for a while. And then some discussion, which is funny because it's not going to be a discussion, it's going to be me talking about things that other people ask. But let's keep this interactive, just ask questions. And he kindly gave me 1 hour and 50 minutes, so we can spend it actually more. So, and there's apparently beer as well. So primer on testing, right? So why do we do testing? We do it essentially to discover problems, right? We want to find bugs. I'm going to try to trick. So we do testing to find bugs, and how do we do that? Well, we try to find bugs with unit testing, property-based testing, chaos testing. There's a variety of different options as well. You can use formal methods, code inspection, and other means of ways to find bugs, but we're going to just focus on testing. So not exhaustive, but unit testing, property-based testing, and chaos testing are probably, and actually, so something like integration testing, I would probably just include in the category of unit testing. So these are the things sort of that we use to find bugs, right? So unit testing, verify that individual components in your program work as intended, and everybody's like, why aren't you talking about unit testing? We know all about that. The important point here is that unit testing is essentially example-based, right? And you in unit tests, you have a picture which is like a pre-state for the test that you run, and then a set of inputs that you write. You write the inputs and give them to a component to assert that that the component stays in some state or give some specific output. So for example, if we were testing a sorting function, maybe I'll just show here. So if we're going to test something like a sorting function, if you're doing unit testing, you will probably have something like, I'm going to test an empty vector, I'm going to test an unsorted vector, and then here you can see the inputs that are coming in, which you handcrafted in while we were writing these tests, and then the assertions basically saying, okay, these are the valid states. Or actually in this case, because there's no state, there's just the output of the function, like these are the outputs that you want. So what are the problems? Well, we don't really explore the state space very much, right? And every test case or every input essentially requires manual work from the developer. So the emoji here indicates that this is not good. But we all know, like if we wrote unit tests and integration tests, like I've seen projects which don't have any, but also seen ones that have way too many, right? So a lot of unit tests or integration tests, and then are they catching any interesting bugs? I think in the end, probably not. Let's try to adjust this a little bit more. Yeah. So what can we do something better? Well, there's something called property-based testing. Instead of testing by example, we specify some properties that the system is supposed to hold. Maybe it sounds a little bit abstract. But basically what you get is with these property-based tests, the test framework actually generates the input. And I need the technician. and just stay there and hold. Okay, no, it's not. So the test framework itself generates the inputs and verifies these developer-defined properties. And actually, it has a lot of these frameworks that do property-based testing, like check, for example, they shrink the test failure case for faster debugging. So they will find something, and they basically kind of randomized inputs, and then once they discover something, they add in to sort of minimize the reproduction, right? So, for example, let's test the same sort function. And now there's no examples, right? There is this property is sorted, which is with this beautiful open-coded loop, which hopefully is correct. But basically what it's saying here, like if you go back and remember what we did in unit test, like we specified the input. We don't specify the input. This macro here will generate something. And basically it will let the framework generate a bunch of different random vectors. And then we call the thing that we want to test, the sort function, which actually now mutates the vector. And then we're going to check if all the elements that we sort are in the correct order, and if not, we will return failure. And then basically when you run this with quick check, for example, it will, for example, generate 100 different vectors with random numbers and random lengths. It will hopefully find empty vectors and all that stuff. And then if your sorting function has a bug, this thing will find. Well, what's the problem with this? Well, it can be actually pretty hard to discover interesting bugs with this, because typically those happen with the interaction with different components, right? So, and I don't know if other people have different kinds of experiences. There was a point in time I really loved property-based testing. I kind of stopped doing that because typically, it is really great for examples where you have a function, for example, that you're testing. It's kind of simple. But if you're sort of building something bigger with multiple components, like what is the property of the system that you wanna test, right? So can we do something else or in addition? So chaos testing. How many of you have heard of chaos testing? A lot of people. So basically, it's a way to improve reliability by intentionally breaking the system, causing disruptions and failures in a controlled environment. I know some folks do this in production as well. I think Netflix at least was at some point famous for that. But basically, it's in this case, for example, we want to make sure that we have a primary node that, I don't know, it's a database or whatever, and then a backup node, and we have some guarantees that if the primary fails, we're going to fail over. So the way we test this is we have a client talking to the primary, and then we have something I call here Nemesis. I think that's probably established terminology. It will disrupt. So it could, for example, kill the node. Maybe somebody sort of pulls the cable or something, right? And then the way you test this is now from the client, for example, you're going to be monitoring this thing. It's like, are we guaranteed to fail over or not, right? So this is actually really great. So it's really great for finding super interesting bugs. And actually, I used to work for a database company called Scylla back in the day, distributed database. We built a tool like this, and it was great at finding bugs, right? But it's really slow to run, right? You can run it for a week and not discover anything, and then the next week it discovered something, which obviously generates this problem. How are you going to reproduce the problem? So this is the problem with chaos testing. It is insanely great for finding interesting bugs, but it has this limitation. What you ended up doing is you just basically add a bunch of stuff to your application or system code to add some verifications or ways to inspect the thing after a crash. But I think taking the reproducibility aside for a second, this is actually pretty slow. And typically you have to create large clusters and all of that stuff. So just to recap, right? So unit testing, example based, as I mentioned. So hopefully there are no unit test maniacs in this room. Like, I don't think they found very interesting bugs. Right? They can be a great tool for developing stuff, but you don't really find any super interesting bugs. Integration tests maybe, right? But even then, I think you have the same, and I'm sort of putting them in the same category. Even then, I think you're really limited by the input space that you have to craft you just the tests that won't put the system in these weird states that really cause a lot of problems. Property-based testing, I think, can discover really interesting bugs in a component. Haven't seen that happen across the system. Chaos testing, it can find these interesting bugs which we wanted to find, but it's slow and not really reproducible. So what if we could combine property-based testing with chaos testing to find interesting bugs in reproducible way? So any questions so far while I get there? Everybody agrees. Two people at least agree. Well, three, because I also agree. Okay, so jumping to the topic of this talk, deterministic simulation testing. Hopefully now it starts to make sense why I spent this time explaining testing techniques that probably all of you are aware. So how do we find interesting bugs quickly with perfect reproducibility? Maybe I should go into marketing. I think this is a great marketing pitch, actually. But really, how could we do this, right? So deterministic simulation testing tests the system as a whole under simulation with deterministic execution. We will go into specifics of this, right? So unlike chaos testing, which I think is kind of closest to DST in some sense, and I think there's like a sprinkle of property-based as well, a simulated environment allows you to compress time. Everyone's like, what does it mean? It basically allows you to run these simulations much quicker because you don't need the network. You simulate the network. You don't do I/O. You simulate all of this stuff, right? And then the claim here is that it's reproducible. And I didn't invent any of this stuff. Go check out Foundation DB. I think is the one that really pioneered this stuff. They invented their own sort of flavor of C++ in the way they like it's those folks were just insane to some extent. And Tiger Beetle, who is mostly responsible for me even figuring any of the stuff out, they're also crazy. It's insane how they are able to do this. But basically, like that is where these techniques were pioneered essentially. And if we now go and think about like what does it mean from application architecture point of view, so it really is about having a simulated runtime and a real runtime. So here I'm trying to sort of illustrate that you have your application, right? Then you have this runtime, which actually uses the operating system, and like this is what you run in production, and then you're simulating something here, right? And basically what this runtime provides is interfaces that we can simulate deterministically. And I now realize I've said the word deterministic many times. We will get to any questions at this point? Is it too abstract, too high level? Like there should be some objections like, no, this can never work. Like otherwise this won't turn out good. Okay, but well, okay, let's assume it works, right? So how do we do deterministic random testing? So I mentioned that in property-based testing, the framework generates the inputs, right? So in deterministic simulation testing, you have the same thing, right? So you have this randomness, otherwise it makes no sense, right? You want to exercise different code paths. You want to, for example, if we're testing a server application, you want to send requests that are valid, requests that are invalid or corrupted or things like that. You want to simulate network dropping packets and things like that. But you want deterministic, something that always happens exactly the same way, but you want something random. How does that work? Well, the way it works is that every random step that you take comes from a pseudo-random number generator, which actually, although generates a sequence of numbers that look random, they're based on a seed. This is just go and look up on Wikipedia how it works. But basically, it's like the values are random. The distribution of numbers is random, but you can always generate the same sequence based on the seed number. Now, the seed part, keep it in mind because it is going to be critical when we go and build our own DST. But let's just assume that you pick a number at the beginning of execution, and then all the decisions the simulator takes are going to be exactly the same if you have the same seed number. And the way you explore the space is you pick different seeds, right? Now I see some confused faces, which is good. Now I think maybe we're getting somewhere, right? Um, and it's the deterministic execution of the simulator that guarantees that given the same inputs, you get into the same state. So because all the steps we took are predetermined by the seed. So for example, every time we send a request to the server, we make a choice. Let's pick a random number. If it's from 1 to 10, if it's 1, we're going to corrupt the packet. Right? So all of these decisions become deterministic based on the seed, but also the execution guarantees that given these inputs, we're going to transition into the same state, right? So now, hopefully somebody's saying, how do you do this? Because there's a lot of non-deterministic execution. It's actually everywhere, right? So you have I/O. So everybody knows that if I send a network packet, like the TCP layer, for example, can reorder stuff and da. Was that obvious to everyone? Task scheduling. So if you use threads or coroutines or Go routines in Go or future promise, there is scheduling, like the actual thing that you run your application on doesn't guarantee that you will execute your concurrent things in the same order. Actually, it probably won't. And even if you're just using threads, for example, the operating system will figure out that, hey, actually there's this other program running, so I'm going to use that core, and that other, your Firefox is running while you run, do the simulation. Memory management, right? So the way you allocate memory, it's not deterministic, but basically the placement in memory. Does it well? We can get into if it matters, but it's a source of non-deterministic flow of time, right? So timeouts and things like that. So what is the wall clock time now? Still today, if you use the machine's clock, the clock can go backwards and things like that. So this is also non-deterministic. And then also, funnily enough, random number generation, or actually the entropy that you use is non-deterministic. So, how do we solve this? And the simple answer is we simulate it, right? So, and this will hopefully become, I do understand it's a bit confusing, but it will become apparent when we look at the building our own DSD. But basically, this already probably hints like to all of you. It's like, so you can have your application logic both running in production and simulated, but there's something happens here. Right? Something is some interfaces need to happen which don't allow you to do all of these things. I don't actually remember what my next slide is. Okay, invariance. Well, is this clear? Like, or this is super confusing? Who finds it super confusing? Well, just a little bit. Most people are lying like you. I think he. So invariance. So moving still deeper into how you build your thing. So now you can maybe imagine a simulator which randomly decides what to do. Now I will corrupt this request. Now I will send this request and whatnot. But we kind of have the same problem here as maybe with property-based testing as well. It's like, so, let's say that the application gets into a bad state. Maybe we leak some resource, or we allow 2 requests to be processed in parallel when we are not supposed to do that, or something. So a really key bit, in my opinion, and well, it's not my opinion, it's the opinion of Tiger Beetle folks, is that you should, and now it's mine as well, but you should have invariants, so assertions in your code as much as you humanly can, because this will help you actually discover the bug, right? So the simulator, you do a fair bit of verification in the simulator itself, right? So, if we're going to send an HTTP request, then we will expect an HTTP request back. So you simulate the client, right? And the client can obviously and should check that the HTTP result code is fine and all of that stuff, right? But that is just testing from external, right? It doesn't really help you in. Well, you could run the simulator for a long time and then it corrupts, for example, if you're using some unsafe programming language like SIG, or SIG or C. But a better way is to have these invariants which basically determine within the code itself. Is like, okay, these are valid states, these are not, and this speeds up things, right? Because as soon as the simulator finds a path where it can get that program into such state which shouldn't, um, which is faulty in some way, it will assert out. Now you have the seed. You can run this thing quickly, probably in seconds or tens of seconds, and you can quickly get to the state with the simulator. And now you can, for example, run a debugger with it, like just step through. So the more invariance you have in your code, that sort of the more high uh, sort of the better results essentially you get from the simulator. Right. Okay. There's a question from the audience for all you folks watching the stream. The mic is not trying to explain to the old people who are like, what the hell is going on? Yeah, just ask. I can also. Good question. So the question, just in case people didn't, so how do you figure out which invariants to use? I think a lot of developers maybe today are already writing those invariants in the unit tests, essentially, just like from testing from outside. Because what you do with unit testing typically is you test these components in isolation, and then what you want to do there, or what you try to do, is you try to make sure that if the components get into a bad state, there's some nasty crash, and then you kind of build the application by assuming you figured all the components are fine, and then you just combine them together. So the way I would think about this is like, so what are the things that you would, for example, write an example-based unit test? For example, like super simple stuff. If you get some value to a function that is never supposed to be negative, you can, by the way, fix it with the type system as well, right? You just don't allow that thing to happen. So maybe, but let's just use this as an example. So if you don't want to allow a negative value, actually it could be like any input that you get that is not valid for whatever reason. You check that. You run a assertion for that. Um, but maybe even more. So that's kind of the way and you can also, by the way, add invariance for the outputs as well, right? If you have some constraint, this function should never return a number. It always has to be between 0 and 100, right? So you can really think defensively like this as well. But I think maybe that the biggest benefit is if you know there is some state that the application should never get into. Well, for example, if you have bookkeeping for some metadata, for example, and then there's an entry to a database or a file system, and you should never get in a state where you have the metadata but you don't have the file or something like that. Like these kinds of super application specific things, right? So that's really and maybe thinking about like states which could really lead to catastrophic sort of results. Like for example, if you're doing retries, sending something external, you're doing retries. So what happens when the last one fails? Like what happens then? What is the state that happens then? If you think it should always eventually sort of pass, then have something like that. I don't know if this was a good answer actually, but go ahead. Do you want to give the? Well, yeah. Yeah, kind of. Yes, yes, yeah, yeah, yeah. You will be disappointed when you see the proof of concept, but it will discuss. Yeah, absolutely, absolutely. So yeah, so the question was like, will be discussing how to do something more complicated than just numbers? Is there a question coming?
Thanks. This is super interesting. I'm fascinated. So I'm trying to grasp the context of or what it actually means that the simulator makes it all deterministic, and it's a bit difficult for me, but uh, so I'm just like trying to bend this. So let's take like just as an example, like if we would have a system that or an application that would run like two threads parallel, and then like depending like then these would like sort of interact or cooperate or whatever, and they would be like reading and writing to the same place or something like that,
Mm-hmm.
and then a certain issue would only happen when like when the threads are timed correctly. So like the other thread first and the second one next or whatever.
Mm-hmm.
So I'm like sort of so what I I'm thinking that perhaps what is happening here is that then the simulator sort of makes sure that both of these paths are
Yes,
covered.
yes, yes.
Does this actually turn, and now back like a point, like touching a bit on the on that input thing. So does that actually turn all those like um, system operations or the way the system can sort of, or all the different ways of the system being indeterministic? Does it actually turn those into inputs of your application in a sense? Because then, like, or testing inputs of your testing, because
I
then
think, yeah, I think I would say in, so yeah, so just to first clarify, if you would have two threads, so you couldn't use, well, depending on how you built the simulator, right? And there's actually crazy people, the crazy Foundation DB people built a deterministic hypervisor. So now you can run any application plausibly deterministic, actually, at least according to Loki. But let's get that to, but you wouldn't use operating system threads, right? You would have your your simulated or the runtime that you provide that would have to have that concept of threads. And now what you're saying is like, okay, the different sort of schedulings or the histories of them. So you could randomize this based on the pseudo-random number generator. So you say that, okay, I'm gonna run this one, and then I'm gonna just take a guess or sort of coin flip which one I'm gonna run next. And now the simulator would, based on the seed, give you a deterministic history of the how the threads were run, but they wouldn't be like running deterministically from the point of view of the threads. It could just randomize them, right? So run this first, run that, run the first one, run this multiple times.
right,
What
exactly.
was the and does it become the input for the system? No, because you would still probably run all of this in production non-deterministic. So you still would, like, you wouldn't run this deterministic thing in production,
Exactly, but
but you were
there's
testing, and from testing perspective, all of those things would have to be well, they would be, the seed is the input,
yeah,
right?
exactly. So this would sort of I try to like sort of putting it into my own words. This would sort of become like parameters of the test case.
Yes, but the seed, but
Okay.
here's actually also an important point. Like, this is something we discovered uh, by ourselves. You only want the seed to be the input, because any other input you would need to know for perfect reproducibility. So we had these like configuration options that you could tune, and then it was like, why isn't this reproducing? Like, I built this thing that is perfectly reproducible. Why isn't? Well, because I gave it less memory than the actual one. So what you want to do, for example, if you have memory limits or something like that, that should be randomized. Well, it doesn't have to be like, it can be a constant as well, right? But it could be randomized using the seed, because now you get the, and this is actually part of the that we will show in the code, because it's related to the inputs that you give. And then finally, fault injection. You know, um, so you can find a lot of interesting bugs by injecting faults. And what does this mean? It just means that, for example, you instead of simulating network perfectly, sometimes you make it fail. You make it fail based on this random decision from the seed, and now, you find. I would actually argue that this is probably the most interesting bit. Well, but that interleaving stuff is as well, obviously. But this is super powerful because now you can say, because like with chaos testing as well, how often do you get to test a scenario where, for example, you have 3 nodes and all of a sudden all of them fail at the same time, or one of them has a disk failure, or one of them has a disk failure and one has a network failure? With this kind of simulation approach, you can, it will find all the combinations possible. And also like the ordering in which node fails first and things like that. And then finally, I think it's finally, yes, about DSD. Then we will build our own DSD, which is super exciting. I actually did build it already. So maybe it's exciting for you. But anyway, so you still need to test the real runtime, right? So again, lesson learned, perfectly simulation is perfect. And by the way, I run the simulator for a whole, night, 12 hours or whatever. Right? But actually, what I discovered is in our simulator we use, it will either discover a problem in half a minute, or it will not discover anything. Then you need to improve the simulator. But as I don't know if I'm going to go. Maybe I will. So here, right? So far we talked about how we built this thing and then how we do this thing. The runtime, this is the glue to the real world. You still need to test that, right? So the way I do it is I use fault injection in the real thing and basically, because it's different code, it is essentially code that is untested with the simulator. So that's fundamentals of DSD. Okay, yeah, okay, yeah. So this is the part that Juho always insists me to do, so I should spend as much time in the editor. So let's do that. I do have some slides as well. So let's build our own DSD, right? So in a nutshell, there's an I/O loop. So this is a server. Actually, this is kind of like a database server doing serving SQLite over HTTP, which there may be a product that does this, but we're not going to talk about products. But this is the proof of concept. This is literally how I started out testing this thing. And it's all in Rust because it's the only language I know. So it's true. I can do with C, but it's lots of bugs. But anyway, I/O loop, accepting connection, virtual I/O, and then a little bit about the simulator. And I'm going to actually show the slides first, and then we're just going to jump in. You want to go to GitHub. I archive it because people started to contribute to it, and it's just a proof of concept. Anyway, so I/O loop, right? So maybe the audience is not that familiar with socket programming. To me, this looks beautiful and perfect, but maybe there can be other opinions. Basically, here you can get sort of a sort of brief. And this is actually now. This is not the simulator. This will be the main loop of the server application. Well, actually, if there are JavaScript people that don't like promises, they will like these callbacks, right? So really simple, a couple of key things, right? So this listen here, it's creating a socket, right? And I left it out because this is first thing that you would have to virtualize, right? To listen to some incoming network stuff, this clearly needs to be simulated because it's I/O. Well, it needs to be simulated, and you need to have the option to run it in real. Then this I/O thing, I/O dispatcher, this run once. What does it mean, right? And then within this I/O dispatcher accept. So actually, listen is just about telling the external world that hey, there's a port that I'm listening to. Accept connection. Accept is actually accepting the connection. Accepting connection would look like this, right? So something happens in the I/O accept thing that then calls this callback, and you can see the server socket and its address, and then the connection socket, and I don't know why I didn't call it connection address, but Here we accept a connection, and then interesting bit, this is sort of recursive kind of like now we get the IO dispatcher here. By the way, this is not my invention. This is clear. This is 100% how Tiger Beetle looks like. They just wrote it in Zig, and I did this crappy version in Rust. But this is how it works, right? So now you have this loop which does the run once. We'll get to that, and then something happens, and then there's a connection. We accept it, and then we say, okay, we're going to accept some more connections. So actually, we're accepting a connection at the time in this example. Then we're going to receive something from it, and then there will be a receive callback and all that stuff that does something and will send. And now we're getting to the virtual I/O. So the I/O thing that I was showing you is a trait. It's like an interface. What would you call it in JavaScript? Interface. Well, that's TypeScript. Interface. But anyway, it's a thing that you can have multiple implementations for. And there we have them, like run once, accept, receive, send. This is basically the fundamentals of providing these interfaces and primitives to do deterministic execution in the simulation. Because, you know, for those of you who spend a lot of time with the low-level socket API, accept, receive, send can be perfectly mapped to what the operating system gives you. These are the primitives that the operating system has. But now we virtualize this, right? So now we can simulate. And now we get to the simulator, right? And this is just bits of it, and we'll get into more of the code, right? So here, right? So here we are. Well, maybe people don't read Rust that well. So basically, this is actually now the simulated client sending a message. We get the I/O thing, obviously. We get a socket, right? We you know that's the connection that we have to the simulated server. Then we have a buffer of bytes. We don't need to actually made like a HTTP or whatever, right? Then here, this thing, generate, perform client request fault, right? So we're gonna check if we should do a fault, right? And this context actually has now the pseudo random number generator, and this function determines if we're not going to send a normal request or if we're going to do a faulty request, which is now, extending this nonsense, right? And then here we also in the callbacks we check that we got the normal one or we sent a bad request, right? So it's a super simple example. But basically what you can see here already from the simulator point of view is that again we have only thing that is sort of a parameter to this is the seed, but we can build complex functions to make decisions based on the seed. And there's actually we will probably get a better idea when we look at the code itself, right? And then here's the the rest of the stuff. And here you actually can see an example of an invariant within the simulator. So we're going to check that, because we sent a proper HTTP thing, we're going to get a proper 200 response. How unreadable was all of this? Probably. So let's jump into the code. So here's actually this is the server loop, right? So let's first look at that. Main, that's the entry point. We get some command line parameters. Then we run the server loop, right? What the server loop is doing here, what the server loop is doing here is, well, it has some, it will, depending on the configuration, it can either listen to one socket or two. That's just a detail that we can ignore. Then there's something called resource manager, which is now managing our state. This is application-specific code. Then we have some nonsense about people pressing Ctrl+C. And then basically, here we just keep on running the I/O loop in a row, right? And then actually the way we can see here, for example, how do we, this is now hooking into the socket that is the main one which receives this HTTP request, right? So again, we get the I/O here, and then we will accept, and if it's an accept, right, exactly what we saw in the slides. So this is exactly in the slides. So accept will essentially just call this thing again. Eventually, now we get part, right? Now we actually start to see some code, right? So now we receive this buffer, and we check if the client closed the connection, and then we're going to execute the request, and then all of this stuff, right? So just to give you an idea, like this is how you would like. This is now application logic, which hopefully doesn't look that different to how you, but it's just using this I/O thing, which guarantees the deterministic execution. Then and basically one thing to also notice is that I have two different kind of projects here, the server and the simulator. So these are two different programs, right? So one thing for me as well is like, where is the simulator? It's just a program that you run that hooks up all your application logic into the simulator. So what does the simulator look like? So we have a main, then we take the seed, or if no seed is given, we generate one, right? Then this is super important. If you ever start to do DST, print out the seed. First thing, print out the seed. We actually had a bug, right, where the bug happened in the configuration setup, but we printed out the seed too late. So we could never, we didn't know what was causing the crash. Then similar things as we saw in the application. So there's some kind of duplication in a sense. We create this resource manager, but here in the simulator, we create one database. So this is like a database, right? And then we also simulate the server sockets here, right? We call the exact same function, well, that sort of a component. We hook that same thing. So this is exactly what maybe I should show. Right, so this is exactly what we were looking at just now, right? No, sorry. Right, so this is what we were, in the server code, we drilled from main to here, so that you kind of know how the data flows. So in the simulator, we hook it up here as well, and then main simulation loop. Like it looks really similar, right? It's the same thing. Actually, this simulator runs forever, which kind of sucks, but in any case, this is it, right? And then now you're like, okay, wow, Pekka, what is the big deal? The big deal here is we have the generic I/O, right? And the Tiger Beetle, for example, has this message bus abstraction. I was incapable of using those fancy abstractions, so I simulate sockets here. But basically, this is what you have. You have this. This is all, well, this is not simulation code, sorry, but this is now code that actually then eventually here, oh, not here, somewhere here. Here you can see, right? Between all of these layers of maybe crap, you have this, like here we're calling into the operating system, right? But now if you think about like, why do we have this? We have this abstraction because now we can simulate the whole thing. Right? All of this stuff here is like, this is essentially now simulating the network stack, essentially, right? Who got confused already? This is simulating the network stack. So what happens when you run the simulator is that you hook into all of this code into the thing, and then let's look at the simulator a bit, how it generates the different inputs. But this is how you guarantee deterministic execution. Actually, I think this version might have a bug. I will actually show you a very plausible bug, which now my eyes can see, but it couldn't, right? So what do you think? What do you think happens when you use a hash map? Is iterating through hash map keys deterministic? It's not. It's not guaranteed. So sometimes, even if the seed is the same, you might have slightly different socket ordering, for example, which is more problematic actually for these listeners. Go ahead.
How do you work around with dependencies? Like, I mean, let's currently what we are looking at is code that you basically you create an abstraction on IO, and then you provide that interface into the application, and the application uses the interface, and then you can simulate the IO, and that's nice. So what do you do with the I don't know, perhaps there's nothing you can do, but just like your thoughts on like basically dependencies that do not use
So
IO.
we will actually probably should save some of this for the discussion uh, bit because like this is a typical and you don't necessarily, if you want to do DST, you don't need to necessarily go all in. Again, this is Tiger Beetle, and now my idea. You don't have to do dependencies, or if you do dependencies, you have to make sure that they provide deterministic execution. Or here's also a dirty trick which people doing DST won't tell you. You don't need to be 100% deterministic to be deterministic, which means that actually a lot of times what you're interested in is the externally observable behavior, right? So in this case, like I just happened to use the hash map in the wrong place, right? In many cases, who cares, right? It makes no difference if some hardcore DST folks will say no, this is no, and it will make it can make debugging more difficult, right? Because now, if you think about all the way from the seed to the behavior, any component that is non-deterministic will have a different path and so forth. But in practice, we've used a lot of well, not a lot, but we've used selected dependencies. Oftentimes, um, if the externally observable behavior is deterministic or you don't care, like for example, this also ties into the invariant stuff, right? If you have something that you have a component that is non-deterministic, as long as you can't observe it from external and you don't have an invariant, then you don't really care.
Mm.
But it's a but to be completely fair towards this approach, like this is the way I'm doing it here, and the way Tiger Beetle is doing it's a commitment, right? It's a commitment to then figuring out the depend or building the stuff that you need yourself. Tiger Beetle, for example, has this idea of no dependencies, right? And you can kind of understand why.
Okay. Can you also do like some sort of, I mean, like just thinking out loud, like some mocking, then like in the simulation environment, like basically don't use the actual dependency, but
Yes.
yeah.
Yeah. So the reason I like this approach is because you get to decide the level of virtualization, essentially, right? So if you need to talk to, I don't know, S3 or a database, right? So you can basically mock that in the simulation. It again depends on what you wanna test. Um, and then finally, before we move to the discussion section, which is not about discussing, but me talking some more. Um, do I have any good? I probably don't have any. Just trying to find. Okay, so this so to answer your question, this proof of concept really doesn't have a lot of good examples on the data generation. So essentially, unfortunately, I told you you would be disappointed. So, from that perspective, you're not disappointed because you. But well, actually, no. But okay. I've forgotten. I left sort of a nice exercise for us. Well, maybe it's just running. Right? So I injected some interesting things for us too. So let's run the simulator. Right, and I told you that it sucks a little bit. So you can see here, starting simulation with seed, right, and it doesn't really print any stuff by default. And then you can. One thing which is also super helpful is you have a lot of like this tracing stuff. So this really helps you when. So you run the simulator, and then if you discover something, then you turn on the tracing. And by the way, tracing can also introduce non-deterministic. So, but basically, I disabled something here, right? So I'm going to show you. So I had disabled fuzzing. So now we're going to run the simulator. Okay, we're not getting anything from this seed or not. So what does it look like for the simulator to find something? So I injected a bug, and then I actually disabled the part about the simulator that found the bug. So now I brought back, and this is essentially, this is what you start out with, right? So now we have the seed here, and we can actually give it, right? And we'll run the same thing. And then this is now supposed to be the deterministic thing. And you could basically, we're not going to verify it, but you could, right? So you could just run the trace, and the two different traces should be there. But we can, I'm afraid to do this because maybe it will discover some. Well, luckily it looks, if you quickly look, it looks the same, right? But this is the key bit, right? Because now this tracing shows you that it ran the same steps and it discovered something, right? So the bug I actually introduced was, well, maybe I can. Yeah, so here we can see this is actually now in the server code, right? So, when we get probably an empty buffer or a bad buffer, right? So this unwrap crashes the thing. So bad error handling essentially, and then the bug that I added was essentially right. So that's the line. So I introduced the bug by removing error handling, right? So, but basically, once we added this improvement, right? And this is a terrible example, but it will just look super lame. But this is essentially what it's doing. So this gen perform client fault, right? This is what you do, right? So here we have the pseudo random number generator, and we generate a Boolean, right? So on a probability of 0.9, so 90% of the time, it's going to be true, and we generate this thing. Otherwise, we generate that thing. If you have a data structure, for example, maybe the normal one would have, I don't know, a string or something. Is it me or no? So you just keep on using this RNG. Like you generate booleans, you generate integers, you generate these bigger data structures like that. You can have helper functions that generate these things given this thing. And whatever comes out of this, right, it is derived from the seed. So this guarantees that for every run that you run, you get the exact same thing. Yes. Yes. Yeah, because it's a. Uh, yeah, no, you're not misunderstanding. That's exactly right. So the reason you don't need it to be a tree is because the deterministic execution guarantees that you can flatten the tree, right? So because you are thinking that, okay, I pick one, I get 1 and 2, or and this is a path that I take, right? And then I take 1 and 2 and another path. So every run once, it's a deterministic step, right? Which picks the sort of the path that you take, and now you're there in the tree, right? So the simulation doesn't run through the whole tree. It will essentially just figure out, I'm going to take this branch, I'm going to take that branch, I'm going to. So it is a linear walk, but it's a tree because if you take another seed, this is how you actually run. So one run is always basically going through the same path, right? And even that can, it can travel a lot and fine. But the reality is that it will be limited, right? So what the Tiger Beetle folks, for example, are doing, and I told you guys they're crazy. They're buying these or renting these boxes from Hetzner with 24 cores and many of them, right? And they're running this simulation for weeks. And they run it for, I don't know, I think individual run takes like a half a minute or something like that. They keep sort of scanning through the seeds, right? So it is not a tree in a sense that one run only traverses through one path of the tree. And then when you pick a different seed, you get to a different path. Good question. I hope so. Okay, anything? Well, am I running out of time? Why did you? Oh no. So yeah. So in the simulator you have, but you understand that in the presentation I paint a nice picture and then I write code like it's like, but maybe he didn't. So here's example from the simulator invariant, right? So here we are sending the bad request, which is a ++, and we expect to get a bad request, or HTTP 400, which is bad request. Here we do the same thing for a good request, essentially, that's HTTP. I don't know if I have any assertions in the server code. Yes, I don't know if I have. I probably don't have any. But if you would scan the code and find well, here's an unwrap. Okay, here you go. Right. So this is essentially an assertion, right? Because in Rust, what this will do is it will try to create this directory or this whole path, and if it fails, unwrap will panic the thing. Yeah. Yes. So that's it. Like, so if the simulator would discover a path, like to me the cool thing is that like you don't really mutate the state in a sense, but if there's a request, for example, which would have a database name, we actually use the same name all the time, right? But you could generate that name, and then if there's an HTTP request coming in with a terrible name that happens to trip this over, like some characters that the file system doesn't like or whatever, this unwrap essentially kills the whole thing. So now you would get the similar result as we saw with the other one. And now I have the seed, and when you give the same seed, it's supposed to generate the same name, plus any additional steps you had to take to get there, right? Because sometimes, for example, in validation, you might have bugs where, depending on the previous state or depending on the other input, you might trigger it or you might not, right? So it's like, well, actually, now I'm gonna, any questions of this? Otherwise, I'm gonna jump. Well, yes.
So when writing the production code, you kind of seem to use kind of a fail path.
I would. This is just me. Yeah, this is. Yeah, so this is just me being super lazy because you can no, but you can. In all fairness, this is a proof of course. No, but if you look at this, right? So actually, you don't want your server to do this, right? But that's also kind of the point of the simulation testing. It's like, and the question about the invariance is like, what kind of, and especially if something is input that the client controls, you probably don't want to crash the server, right? But as you're writing the code, if you're lazy like I was here, this is better than just silently, whatever, right? Because now I will be able to trigger this somehow and then fix it. But yeah, exactly. Any other questions? Oh, go ahead. Mhm. Yeah, yeah. So yeah, um, great question. Essentially all we have right now is this sad thing, right? So what you would probably do is like something like, I don't know, a database name, right, and then gen database, right, and then you would do right, and then cursor will write that stuff, right? But this is essentially what you would do. This is how I write code these days, by the way. So, but well, I let the. But basically, here's the thing, right? So this is what you do. You have these functions, and basically what I learned after all of this stuff is like you probably should just randomize everything, right? Any data that you have as an input, just write a function like this, right? do. But this is probably super familiar to people who have done unit tests, right? You often have these kinds of like, because either you always use the same value across all of your tests, or you're just like, I'm gonna do this, generate whatever customer name or customer email and stuff like that. So this, I don't know if this answers your question, but this is what you do. It's like manual work in a sense. Yeah. Yeah. So in this case, actually, so because this is kind of like straightforward, send a request, get a response back. So you probably don't need much more than a function telling, okay, this is the request that I generated, and because I have the callback model, maybe you should give you the callback as well, right? And then in the loop, well, actually, maybe I have. Mm, yeah, so you can see here a lot of layers. Oh, wrote this. Let's even recursive. Wow. But if we go, well, actually, so the way it works here is, so you could, for example, have the inputs being injected here, right? So uh, send client, right? This that would be probably, I think we probably do it like this, right? So now you can kind of, you know, and by the way, you would probably randomize this as well, right? You don't want to do it every time. You give it some probability, and then sometimes do it and sometimes don't, right? But in any case, so you would do something like this, and then now you would call that function to generate the request, and then that request itself would be randomly generating one of the different cases that exist, and so forth. So and then you would also basically need to have the invariance of the checks that you have based on the response that you get. In practice, I think maybe we have. Well, this is kind of. Well, this is this doesn't have it, but basically what you end up having is the the simulator is essentially like a state machine, right? So you start with the state where there's no clients, it's just a server, right? Then you do a step, which is randomized step to update the state machine to, for example, that we're going to have 3 clients, like randomized that we are going to have 3 clients, and all of them are initial state. You step again, now 2 of them are going to connect, and so forth, right? And then, final step is now I sent the request, and I'm going to wait for a response, and then I'm going to validate that it's what I was expecting. And now remember, the IO thing could just drop your request, right? So it could that never comes, and then you need some timeouts in the client code, and so forth. And then you also need to check if those timeouts are what is kind of, because it can happen in real world situations as well, right? So the server just doesn't respond, right? So then, like, is that timeout in a controlled fashion, or is it a bug, and so.
Okay, very good. So here's a private deal that's by DSP system,
Mm-hmm.
which is built around the IO
Mm-hmm.
abstraction. So is that kind of a, so like if I want to do DSP on an existing system,
Mm-hmm.
is that the abstraction I have to re-architect my system or to make it work? Or are there like, what about other sources of IO? Do I have to kind of re-architect my interfaces to lend themselves to this type of application structure? How would I go about implementing this in an existing system?
Great question. What I tend to do when I'm running out of time to do slides, I on X ask people to what they would want to see. So kind of preempted that question in a sense. So one good question was, can you do DSD incrementally on existing code bases? I think it's kind of similar. So you were asking, what just need a fresh rewrite? What are the architectural prerequisites, and then when to use DSD and not? So um, I'm a newbie in a sense, right? And I got bitten by the tiger beetle bug. So I think DSD is probably easiest to adopt if you're building something from scratch, and then you build something like I did there. But there are existing frameworks and tools out there that let you adopt DSD, right? Um, And I actually don't know if there's, so I don't know what kind of languages or frameworks you're using, but Tokyo in Rust is a really popular like async await or asynchronous sort of server application framework. So there's a framework called Turmoil from AWS, I believe, where they uh, turn those Rust applications into something that you execute deterministically. There's still a lot of code that you have to write yourself in terms of the inputs and so forth. But here's the reason they can do that, because if you think about us, and this future promise is probably should be, well, I don't know what it would mean to do this for JavaScript, but because future promises essentially is a chain of things that you execute, and then some of them might have to be deferred and then rescheduled. So the Docker is essentially like a task scheduling machine, right? So the tasks are the futures essentially. So you can schedule them deterministically. You can virtualize at that layer, right? So what Turmoil, for example, gives you, it gives you Tokyo interface, but that executes deterministically, and plus some other stuff that you can do to wire up. So that's what you can do. And I already mentioned the crazy Foundation DB folks doing a tool called Antithesis. And they're not even sponsoring me, so. But we're actually almost certainly going to use the tool, because you can use things like this to test your. And I know we weren't supposed to talk about products, so forget about the product. But the thing, and I have no stake in here, but what they are saying is that you can actually do this deterministic stuff at the operating system level, right? So now you can run whatever thing you have, and they claim to guarantee that it's deterministic. But anyway, they have the same. Obviously, they have the same keywords here, right? Because this is what these are folks that did Foundation DB. What they essentially did initially for Foundation DB is that they built the simulator first. I think they built most of the simulator before they ever run any production code. They had a extension to C++ to make sure that you can write that stuff. And and now a decade later, they are doing this. So there are options to do DSD even if you don't go full DSD yourself. Yeah, I don't have any experience doing it. Besides, I tried Turmoil. You know, I ended up building the thing myself. Any questions? So, all the questions. It's good that we have 1 more hour. I need more beer. So.
So if you need to proceed, it's like a random walk. Right?
Yes.
And how do you convert?
Uh,
When do we know it's enough? There's no bug. Or
when do we know? Right. Well, actually, I think we had yeah. That's in the beginning. I think I cited somebody who was much more right. So, but it's a good question. So my experience so far has been that. So first of all, the simulator we have is super simple, and every time we teach it a new trick, it finds some bug. So it's kind of a question, not so running is one, but also like what is the coverage of the simulator? And one thing which I would love to see is like code coverage or something like that. I haven't found the tooling, but even that doesn't tell you, because what you essentially want to find is like when did you exhaust the state space, and then if you have multiple things. All I can say is that Tiger Beetle still keeps running their stuff for all the time essentially. I'm a computer scientist. No, I don't. Yeah. Yeah. For what we do, for example, is we run the simulator for 30 or 60 seconds, and then we switch to another seed. Because that's also a factor, like how far do you want to walk, and right, yeah. So, if I have to be honest, uh, I don't know what. Like the Tiger Beetle folks, I think are giving, but also the Antithesis folks are running this stuff all the time. So plausibly, the way to think about it is that you should never assume to have exhausted the state space. in practice, if your application survives this kind of a simulator for a week, which is, well, one thing which you can calculate is like how much testing you got done compared to like chaos testing. So like if we would tell you that I ran this chaos testing for this system for 100 years, right? So you will probably have high confidence. So that's kind of what you aim towards with this, because now you're cheating, right? But you're saying I simulated 100 years of testing. But great question. Maybe it was a too good question because I don't have a. But yeah, I don't know. I don't know where that where. No, I think with this stuff, your approach is going to be really practical in terms of like, for me, it is essentially if it's like once I left it running for the whole weekend by accident, and then Monday morning, like, okay, it didn't find anything, must be perfect, and it is pretty perfect in this sort of state space that the simulator finds. So now I'm thinking every time I can't find any bugs, it's probably that the simulator sucks, right? Then there was a question about DST bugs found, real life examples of bugs you have found. I found a lot of bugs, mostly edge cases. I'm just going to cite Tiger Beetle because they had, like in my project, like pretty much any edge case that you forgot about the simulator found. Just off by once or whatever. Protocol handling, data corruption, and more. I was looking at the Git logs. But what Tiger Beetle is doing is finding bugs in that cause data corruption. They simulate all kinds of faults in the disks and in the network as well. The craziest thing I heard, and I mentioned many times, is they're performance testing the stuff with DST because they can provide some properties that they want to test in. Yeah, go ahead.
That's really good question. So I'm curious about how does it learn
So basically, two ways. One of them is that the simulator is able to verify the output, right? So the simulator, so in request response model, like the simulator knows this is the request I sent, and my expectation is that this is what I get back, right? And then you verify in the simulator that you get this thing back. If you get something wrong, then that's end of the simulation. You found something. The other thing is essentially crash is essentially about the invariance, right? So you bake this stuff into your application code that like this should never ever happen, right? And but like I think intuitively a lot of people when they write code, like they know, like nobody's supposed to call this function with this thing, right? Or this should never be null or whatever, right? So if you add an assertion there, but in strongly typed languages, you typically get a crash anyway, a nice crash. So maybe that the assertion thing is more for, but it's a nice, because like you can sort of do invariance on so many things. Like, is the internal state consistent, right? This is what I expected. It's kind of defensive. Okay, go in this case, yes. Yes, exactly. So but that is the externally visible thing that you validate, and you validate it in the simulator because you are now essentially taking the perspective of the client, right? But if you can validate some things within the server as well, like this, like and then that is essentially just an assertion that you. Yes. 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 Absolutely. And there are things like time traveling debuggers as well, which is kind of the similar thing. I think for me, DST is so powerful because once you build this separation and you do the simulation, the compression of time is essentially the value here, which you maybe don't get with this. But yeah, but that's actually related. Good point as well. Like when you're doing chaos testing, for example. the minute you find your first interesting bug that you can't reproduce, and then you just have to, tell people that, unfortunately, all we could do is make the code more robust. So the next time this triggers, we will know more, and you will never know more, right? Because it will never ever. But these are typically things that will never ever trigger, except in production. In your best customer loses their data or whatever. So DST is really, I think, geared towards also finding those weird things that because sometimes like I've heard it so many times from developers like, yeah, it's off one time fluke, right? It's we don't really know why it happened, and then it was like, yeah, it looks really fishy, maybe blah 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 blah, stack got corrupted or whatever, and everybody's happy. It's like, yeah, we try as it works, and then everybody forgets about it. 1 year later in production, boom, you get the same crash. Like what? Because these are things that rarely happen. Like, now I'm not taking any more questions. DST bugs found, so we covered that a little bit. Flow of time. Um, so this is actually a question which I probably didn't talk about a lot. And if you looked at the simulator I showed you, it had no concept of time. Because the server was never asking for the time, right? So there was no logic that was dependent on time. So all of this was implicit. The simple answer here is that every tick becomes a increment or decrement in time, because sometimes you want to simulate the clocks going backwards, right? So every time you do this server step, the clock goes forward or backward or stays the same. How much? Maybe you want it to make it static. I think Tiger Beetle tries to do it in a way where they guarantee that the actual server always runs like 250 milliseconds each time or something like that, right? So the actual production server runs for a specific time duration. So in simulation, you simulate the clock as much. The honest answer is I don't know what's a good strategy. The way we did it is in I/O, you now have a method called get current time, right? And then you vary this in the simulator, and then in production code, you just get the values of the. So sorry, Alex, for this terrible answer. Yeah, so here I'm just basically saying the same. Pitfalls and gotchas. I did mention some of these things, probably many times. But it is super easy to introduce non-deterministic behavior, like really. And I should have known about the hash map because I was talking to I forgot whom, and they were making this point about you sort of showing this code example in Go where you iterate over a hash map keys, and then it's not deterministic. And I was brave enough to say I don't care. Because it is not necessarily externally observable, right? But in our case, it was, and it turned into a bug. And by the way, so these are unfortunate bugs, right? Because now the same seed doesn't generate the same thing. But in practice, you probably still are going to hit the bug if it's just going to be with some other seed. So, but yeah, like this is something really to watch out for. Another thing is that the simulator is both relentless and limited. And what I mean by that is that if it knows about some trick, some way to generate input that can get the server into bad state, it will definitely find, almost certainly. But it can also give you this false confidence because maybe your simulator is just total nonsense crap as the one we saw, and it won't find anything. And still the simulator will say, and you can tell yourself a story where you said, I ran it for a week and it didn't find anything, let's ship it, right? And it's only didn't find anything only because your simulator is so limited. So that's one pitfall. And then let's just close. We can keep talking, that's fine. But anyway, so DST is powerful technique for finding interesting bugs quickly with perfect reproducibility. And then, as I mentioned, the key bit for me is like you have this seed that generates the input randomly and also the different paths. And then basically the deterministic execution guarantees that you are always going through the same state changes. I think that's more or less very simple. We can keep talking if we have more questions.
You don't have feed for the feed, so you generate all the same feed.
You don't have seed for the seed. I don't know if you, yeah. So the way I just have this shell script that runs the simulator, in a loop, and the simulator itself generates the seed. So, but you can never run the same thing. But you don't care because like what you care is just finding one seed and any more questions? Go ahead.
Hey, so I was wondering, like, how deep can you go in practice? If I have an application with like hundreds of different things you can do, and the state needs to be like really complex to kind of convert do you feel like with the patience
I think it's just a lot of work, right? So like I was dissing unit testing in the beginning to some extent, but I think that the thing that you are doing there is the stream still on? No, it is. Okay, I just don't see it. So yeah, I'm just watching black. But if people can hear me, so uh, unit testing really, like a lot of times the way you write good unit test is you have good ways to generate the fixture, right? The base state essentially. So it's work, plausibly a lot of work. Um, the cool bit is that you tend to, because like when I say things should be randomized, that's half truth, right? Because you don't want things to be totally random. You want some randomness, but for example, if you have, let's say, username or email, like they need to, you want to generate a valid email address and an invalid email address and all those things. But I don't see a fundamental limitation in like again, the more you put effort into generating inputs that are interesting, the more likely it will find. But also, I think the assertions in the application code itself are critical. But it's a question of like what kind of guarantees you want. Eventually, like if you let the application go into a bad state, some of the requests will start failing because it's for an application to get in a bad state, it probably needs to have some bad observable behavior. So maybe it starts returning the wrong results or something like that. So you will eventually discover those. But just to put a disclaimer, like the complexity of what we're doing with this is still kind of limited. Like I think we could probably still understand, well, like kind of, or at least fool ourselves into thinking that we understand the state space. Like not exactly obviously, but we can understand what the different parts are.
yeah. Actually, people who write in memory and security, just like me, and open source, like training and all this stuff, we use something like Google's cluster code.
Yeah, yeah, yeah.
It's very undeterministic. It's very good for finding wrong user input,
Yeah.
memory input, stuff like that, all
Yes.
this kind of thing. So that's quite undeterministic. I'm trying to find out what uses this one is very good at. Like, as a good example, I think like the job is very good at memory assessment,
Yeah.
wrong user input, this kind
Yeah.
of thing. And so everything I do within this software unit testing, it will generate on its own the
Yeah.
test system.
Yeah.
It just needs a lot of code here.
Yeah.
In this case, what this approach can
Yeah, but I think it's just a matter of sort of level of testing or perspective of testing, because I think still what you are describing is mostly towards um, somehow verifying that the individual components, or maybe there are multiple components, but definitely a single machine, right? So a lot of this stuff is, once you go like distributed system, which all you really need is a client and a server, right? I think this already opens up so many, like, I think DST is mostly for finding the most interesting bugs, right? So these bugs, while they're bugs, they are not like, by interesting I mean things that you would not think of, right? So I think these fuzzers, for example, are automating things that, and I'm not saying people should do it, obviously not. it's good to use not disputing that, but like they won't find things like what happens when you have a failover and actually the backup server is not responding and there's a network, or like I think those are just more complicated use cases, or scenarios which I think this is super powerful. But also I think fuzzers have kind of this limitation that they are super focused on generating bad input, and bad inputs don't put the system into weird states. Like I think what happens with the system is that like maybe initially the system might accept few rounds of bad inputs and then it corrupts itself and then you're happy. But I think once you're done with that phase, what will almost certainly happen is you fix your validation and then every bad input is rejected. And then the interesting bugs are going to be interactions between good requests that pass the validation and then maybe you throw in a bad one in the mix. That is at least how I think about it. I have not, and I don't know. I don't know what would be involved. It's a good question. I don't know. I think it might be hard because it is so in property based. Well, actually, I don't even know how they do it. So maybe I'll just shut up and say I don't know.
Well, I had the same question, and I have like this free idea for you. So how they do it in property-based testing in some libraries is that random generator gives you this stream of bits. So then you just print the stream of bits to
Oh,
the zero. And you could put it that in the system.
right. Okay. Yeah.
Yeah, I have no idea. This kind of testing.
Yeah, that's it. Yeah. In practice, like I said, typically a failing simulator run for me has taken a second, right? So it hasn't been, but maybe for larger, I should ask the Tiger Beer. So I have the privilege of being the decision maker and the person who did it. So it was easy. I don't know. I think so. To be fair, I think this is it's not a new approach. Like I said, Foundation DB did it already long time ago. It is not a popular technique. Probably the best way is to get them excited about something like antithesis and buy a license and go from there. But I think it's a question also in terms of, for example, if you're using Rust and Tokyo, you could just use a tool like it's just a testing framework. It doesn't really like. I think the scary thing probably for decision makers, like, okay, so you're gonna rewrite everything in this weird style, right? Which is kind of the answer I had to. Well, I'm not the only decision maker. I have a co-founder that I had to convince, and a bunch of other people. But yeah, no good tips in that sense. But I think it's just a question of how you frame this as well, and if you're able to use, like for many applications that if you happen to write it from scratch, I don't know if it makes a big difference to any decision maker. What is the style that you're using? And plausibly for this kind of stuff, so I picked the Tiger Beetle approach, which is essentially you just build everything from scratch. I think there's a case to be made that somebody builds a framework, right, where all the I/O virtualization is built in, and then you just use it, and then all you need to convince people is that it's fine to use this specific open source approach. Depending on organization, it might be hard on it, but yeah, that's pretty much.
Then maybe some is about to have some labels to bit medical device and performance. What is close about the configuration to have this Wi-Fi roaming problem.
Yeah.
Maybe it takes like 2 months to go like it takes us to back in 1 year. So I think that maybe this would be
Yeah, so that's a great. So this is exactly the kind of things that you would hope to find with this. But this is I like to say compressing time because it sounds so fancy, but it's just get the results quicker, right?
So by indexing the there's not reproducible ever. We
Yeah.
extremely able to do super range
Yeah.
and the handlers in the account system.
Yeah.
And when it handles the PV simulation, so basically what we do is just
Yeah.
and this is our company developed like a real simulation.
Yeah.
Taking that equation
Yeah. Absolutely. Yeah. Yeah, but I think maybe decision makers in general just underestimate the, but I'm a developer, so I do this as well. But like underestimate the time it takes to fix a really, really interesting or bad bug. That's a great story, and plausibly you could find it with this. But it's also like a lot of times developers have a intuition. It's like it's probably this thing, that it's this interaction, but then how do you test it? It's like maybe the intuition is that you need these things, like 10 of these things, and that is failing and that is not failing, and so forth, right? So it's just super hard to express this as a test case, right? And in simulation, you kind of don't. You just define these different states that the components can be in, and then the sort of simulator just finds the combinations, essentially. I told you I should be in marketing or sales. This guy's so ready to buy if I just had something to sell. No, but like I think that's but again, I think this is still kind of new approach at large. Yeah.
Have you tried anti-physics yet?
No, we're talking to them to get. So I know roughly how it works. I don't know if I'm allowed to tell you, but basically, well, I can tell you what I know from the public source. So um, hypervisors are basically ways to virtualize a machine, and I use the word virtualized I/O for a reason. So what they and they also changed something in the BSD kernel, I think. So basically, the way it's supposed to work is that for example, all your threads will schedule deterministic. And then they will have a component where it does this, like you have a test suite that you define yourself. It doesn't have to be in this style that I described. It can be just a test suite. And then they will randomize that as well. And then basically, it is kind of, well, it is this approach, right? But they do it at such a low level or low layer that you can build whatever or test whatever applications on top of it. The reason we want to use antithesis is because we actually talked to the Tiger Beetle founder, Joran, and we had these naive questions like, should we go all DST or just use the product, which we are not going to mention, antithesis? And he said you should do both, right? And we're like, well, and the point was made like if you control the DST yourself, it is super powerful because now you get to do a lot of interesting things with the simulator. What you can get with the tool like antithesis is essentially testing the simulator, right? Because now you can find those non-deterministic behaviors that you introduce in the simulation. But unfortunately, we don't have any actual usage of antithesis right now. So I think we are close to. I think we exhausted the questions. Thank you, everyone.